In part 3, we trained a neural network. Forward pass, compute the loss, compute the gradient, update weights, repeat. But we skipped a step. We said compute the gradient, like it was easy. It's not. The gradient tells you which direction is downhill for every weight in the network. With 5 weights, you could figure that out by hand. With 1,000,000 weights, you need an algorithm. Here's one way to do it. Pick a weight. Nudge it up by a tiny amount. Run a forward pass, get the loss. Nudge it back down, run another forward pass, get the new loss. The difference tells you the gradient for that one weight. Now repeat for every other weight. With 1,000,000 weights, that's 2,000,000 forward passes for a single gradient update. Then you update the weights and do it all over again. Next update, another 2,000,000. It works, but it's impossibly slow. Training would take years. There's a faster way, but it requires looking at the network differently. A neural network isn't a black box. It's a chain of simple operations. Take an input, multiply by a weight, add a bias, pass through an activation function. The output of one step feeds into the next. Each step on its own is simple. The chain is what makes it powerful. And there's a rule from calculus that tells you exactly how to handle a chain of functions. Say you have two functions chained together. X goes into G, and G's output goes into F. You want to know, if I change X, how much does the final output change? The chain rule says, multiply the two rates of change. How fast does F change when G changes, times how fast does G change when X changes? Local rate times. Local rate gives you the total rate. It works for any number of steps. 3 functions chained together, multiply 3 local rates. 10 functions, multiply 10. 100-layer network, multiply 100 local rates. Each step only needs to know its own derivative. The chain rule links them all together. Let's make this concrete. Here's a tiny network. 1 input, 1 weight, 1 bias, 1 activation, and a loss at the end. We'll redraw it as a computational graph. Each node does 1 operation. Multiply, add, activate, compute loss. Data flows left to right. Let's push numbers through. Input X equals 2. Weight W equals 0.5. Multiply, 2 times 0.5 equals 1. Add bias B equals 0.3. 1 plus 0.3 equals 1.3. ReLU. 1.3 is positive, so it passes through unchanged. Output, 1.3. The target is 1.0. Loss equals prediction minus truth squared. 1.3 minus 1.0 is 0.3. Squared, 0.09. Every node stored its values during the forward pass. We'll need those in a second. Now we go backward. Start at the loss. The loss is the squared error, so its derivative with respect to the prediction is 2 times the error. 2 times 0.3 equals 0.6. That's the gradient signal. It starts flowing backward. It hits the ReLU node. ReLU's rule is simple. If the input was positive, pass the gradient through. If it was negative or 0, block it. During the forward pass, the input was 1.3. Positive, so the gradient passes through. Still 0.6. Next, the add node. Addition distributes the gradient equally. Both inputs get the same gradient. 0.6. So the bias gets a gradient of 0.6. And the multiply node's output also gets 0.6. The multiply node is where it gets useful. Remember, this node computed X times W 2 times 0.5. To get the gradient for W, you multiply the incoming gradient by the other input, X. 0.6 times 2 equals 1.2. That's the gradient for the weight. To get the gradient for X, you multiply the incoming gradient by W. 0.6 times 0.5 equals 0.3. And that's it. 1 pass forward, 1 pass backward, and we have the gradient for every parameter. The weight's gradient is 1.2. The bias gradient is 0.6. We didn't wiggle anything. We didn't run extra forward passes. The chain rule gave us everything in one shot. Our example had one weight and one bias. A real network has millions, but the algorithm is identical. Forward pass, push data through, store every intermediate value. Backward pass, start from the loss, multiply local gradients at each node, and propagate backward. By the time you reach the first layer, every weight in the network has its gradient. Compare this to the naive approach. Wiggling each weight, 2 million forward passes per update. Backpropagation, 1 forward pass plus 1 backward pass. 2 passes total. Same result. The speedup is a factor of 1,000,000. That's why deep learning is possible. Without backprop, training a large network would take longer than a human lifetime. Now we can fill in the missing piece. The training loop from part 3 had 4 steps. Step 1, forward pass. Push data through the network, get predictions. Step 2, compute the loss. How wrong were the predictions? Step 3, backward pass. Backpropagation sends gradients from the loss all the way back to every weight. Step 4, update. Nudge each weight in its downhill direction. No hand-waving left. Every step is accounted for. This is the complete algorithm for training a neural network. Forward, loss, backward, update. Every language model, every image classifier, every AI you've ever used was trained by running this loop millions of times. The details vary, but the core is always the same. That's backpropagation. The chain rule lets you decompose a complex derivative into a product of simple local derivatives. A computational graph organizes the network into a sequence of operations. The forward pass computes outputs and stores intermediate values. The backward pass multiplies local gradients from the loss all the way back to every weight. 1 forward pass, 1 backward pass, all gradients computed. That wraps up the fundamentals. We started with a single neuron, built it into a network, learned how to train it, and now we know how gradients flow backward to make training efficient. So far, every neuron connects to every neuron in the next layer. That works for small inputs. But what about images? A single photo has hundreds of thousands of pixels. Connecting every pixel to every neuron in the next layer would mean billions of weights. There's a smarter design that only looks at small patches at a time. That's part 5, convolutional neural networks.